The game of cops and robbers on graphs is a simple two-player game played on a graph, where one player represents a team of cops and the other player represents a single robber. The objective of the cops is to capture the robber by moving their cops around the graph, and the objective of the robber is to evade capture by the cops. The game is played on an undirected graph G, which consists of a set of vertices and a set of edges. The cop and robber start at chosen vertices on the graph, and the cops take turns moving one of their cops along an edge to an adjacent vertex, then the robber moves to the adjacent vertex next. If at any point in the game, one or more cops occupy the same vertex as the robber, the cops win. On the other hand, if the robber can evade the cops indefinitely, the robber wins. By the way, there are only two rules players need to follow. They are simple. First, cops going first. Second, players must move to a neighboring vertex, namely, you can move only one unit each round. A graph is said to be a cop-win graph if there exists a strategy for the cops to capture the robber, no matter where the robber starts or how he moves. Conversely, a graph is said to be a robber-win graph if the robber can always evade capture, regardless of where the cops start or how they move. The minimum number of cops required to win in a graph G is a well-defined positive integer called the cop number of the graph G. We write C, G, for the cop number of a graph G. If C, G, equals K, then we say G is K cop win. In the special case K equals 1, we say G is cop win. A graph with C, G, greater than 1 is called robber win, since one cannot capture the robber. Now we know the basic idea of this game. Quiz time. P4 is obviously cop-win graph. Robbers has nowhere to go. Will graph is cop-win 2 because it has a universal vertex. As long as cop choose to start on this vertex or move to this vertex, cop can go to any outer vertices next round. Complete graph of order 6 is cop-win since every vertices of this graph is connected to any other vertices. Now we have the following lemma. For n greater than 0 an integer, we have that C, Pn equals C, Wn equals C, Kn equals 1. Which means they are cop-win graph. Also, if you look at tree graph, it's easy to tell that it is cop-win. Lemma 1.2. A finite tree is cop-win. By the way, cycle graph that has vertices number greater or equal than 4 is robber win. To figure out what exactly going on in a cop-win graph, we can ask ourselves a question: when can the cop win? Or say, what is the sign that players know that they're gonna win? Generally speaking, it's when the robber has no way out, he was backed into a corner. Let us translate this to mathematical language, when there is some vertex v such that n, u, subset of or equal to n, v. Definition. The set of vertices adjacent to v is called the neighborhood of v, denoted n, v. This is sometimes called the open neighborhood of v. To distinguish it from the closed neighborhood of v, n square bracket v square bracket equals n, v, union, v. So what happens at the end of the game? At the end of the game, you have a cop somewhere. A robber somewhere. This is robber last move. After he moves he will be caught no matter what he does, because we are in a cop-win graph. That means there must be an edge here, since if robber decides to stay put, he must be caught, and wherever he can go, the cop can go there as well. Conclusion: the closed neighborhood of robber's vertex is contained in the closed neighborhood of the cop's vertex. Written as n, r, subset of or equal to n, c. This is cop's winning condition. If the robber moved here and if the cop moved to vertex v, then she can anticipate all the moves of r and win in the next round. Such a vertex is called a corner, or a trap, pitfall, or irreducible. More precisely, a vertex U is a corner if there is some vertex V such that n, U, subset of or equal to n, V. The vertex V is said to cover U. We write U approach V and say that V dominates, or covers, U. In this case, consider the second to last move of the cop. The robber could pass, so C must be joined to R. Or the robber could move to a neighboring vertex, so C is joined to each neighbor of R. This proof lemma 2.1. If G is a cop-win graph, then G contains at least one corner. Now we can try to define a cop-win graph. Before that, we need to introduce a concept of dismantleable. A graph is dismantleable if some sequence of deleting corners results in the graph K1. For example, if we keep making corners disappear, only one vertex, K1 left. We can know this graph is dismantleable. Which means this is a cop-win graph. Finally, we have all the conditions to formally define a cop-win graph. Theorem 2.3. A graph is cop-win if and only if it is dismantleable. Notice that this is an if and only if statement, so if a graph is not dismantleable, then it is robber win. Which means you will never find a corner. If you play this game with your friend after you watch this video, you will never lose again. Of course, you have to choose the cop side and draw the picture yourself. Here is the trick: you never draw a circle that has vertices greater than 3. Just start with a single vertex and randomly draw lines. Done. This is a cop-win draw since you can erase all of the corners and end up with K1.